Hi everybody, welcome to Module 5 of Pluralsight course on Modern Software Architecture. Dino Esposito is speaking. About a decade ago, when Eric Evans first introduced domain-driven design, the world of software was such that an object-oriented model to fully express the intricacies of the business domain sounded like a really compelling idea. But years of practice instead have proved that the task was more difficult than the initial estimation. So for years, as developers, we faced a lot of complexity, and we thought that it was all about the inherent complexity of the business model. So with domain-driven design, we focused on practices to facilitate the learning of the business domain. And now we are realizing that there is more to it, and we are seeing a new approach emerging. Today, there is the classic way of expressing the business domain through an object-oriented model, all-encompassing, and there is a new way. The new way goes under the name of Cqrs, which is the acronym for Command and Query Responsibility Segregation, and it's all about separating commands from queries using distinct application stacks. This module discusses the foundation of Cqrs and identifies three flavors of it that I like to call, in growing order of complexity and sophistications, as regular Cqrs, premium Cqrs, and Cqrs Deluxe. Over the past decade, many embarked in projects following the guidelines of domain-driven design. Some projects have been successful, some not. The truth is that a single, all-encompassing object model to cover just any functional and non-functional aspects of a software system is a wonderful utopia, and sometimes it's even close to be an optical illusion. In Module 4, I briefly presented two ways to design a class for a sport match. One that incorporates business rules through the internal state and exposed behavior, and one that was a mere data transfer object, trivial to persist but devoid of business logic and with a public unfiltered read-write interface. In a single, all-encompassing object model perspective, the former class, the one with a rich behavior, with methods like start, finish, and goal, is just perfect, as it faithfully describes the commands that alter the state of the system and the events observed in the real world. But are you sure that the same class would work well in a plain query scenario? When your user interface just requires to show the current score of a given match and that's it, is such a behavior-rich class appropriate? Obviously, another simpler match class would be desirable to have, especially if it acts as a plain data transfer object. So the question is, should you have both? Or should you manage to disable effects of methods in query scenarios? In a single domain model scenario, none of the classes shown now are perfect, even though both can be adapted and used in a system that just does what it's supposed to do. The behavior-rich class is great in use cases in which the state of the system is being altered. The other is an excellent choice instead when the state of the system is being reported. The behavior-rich class requires fixes to fully support persistence via an ORM, and if used in a reading scenario, it would expose behavior to the presentation layer, which could be risky. The other class has no business rules implemented inside, and because of its public getters and setters, is at risk of generating inconsistent instances. Defining a single class for commands and queries may be challenging, and you realistically can get it only at the cost of compromises. But compromises may be acceptable. Treating commands and queries differently through different stacks, however, is probably a better idea. And this is Cqrs, Command and Query Responsibility Segregation. A command is then defined as an action that alters the state of the system and doesn't return data. A query, instead, is an action that reads and returns data and doesn't alter in any way the state of the system. All that Cqrs is all about is then implementing the final system so that both responsibilities are distinct and have each its own implementation. This is actually nothing new. Back in the 80s, Bertrand Meyer already said that in software any action can either be a command or a query, but never both things. In terms of layers and system architecture, with Cqrs we move from a classic multi-layer architecture with presentation, application, domain, and infrastructure, as we discussed in Module 3 and 4, to a slightly different layout. In the new layout, presentation and infrastructure are for the most part unchanged. The application is crucial to have in the command stack, but can be considered optional in the query stack. The huge difference, however, is the implementation of the domain layer. In Cqrs, you may need to design a domain model only for the command stack and can rely on plain DTOs and direct data access in the query stack. Why is Cqrs then good for architects to consider? Major benefits are that separation of stacks allow for parallel and independent development, which means reuse of skills and people, and freedom to choose the most appropriate technologies without constraints. In addition, separation of stacks enables a distinct optimization of the same stacks and lays the ground for scalability potential. Has a pleasant side effect, the overall design of the software becomes simpler, and the refactoring and enhancements comes easier because of the limited common surface existing between commands and queries. Quite simply, Cqrs is a concrete implementation pattern, and it is probably the most appropriate for nearly any type of software applications today, regardless the expected lifespan and complexity. A point that often goes unnoticed is that there is not just one way of doing Cqrs. In particular, for the purposes of this module, I would recognize at least 3 different flavors of Cqrs that I like to nickname after common marketing rules of hotel rooms and drinks. So, regular, premium, and deluxe. Cqrs is not just for overly complex applications, even though it's just there that it shines in concurrent, collaborative, high-traffic, high-scale systems. The principle behind Cqrs works well even with plain old crude applications, create, read, update, delete applications. When it comes to this, so to make an existing crude system Cqrs aware, the application architecture changes slightly like this. Instead of a monolithic block that takes care of database access for reading and writing, you now have 2 distinct blocks, one for commands and database writes, and one for queries and database reads. If you are using Entity Framework or another object relational mapper framework to perform data access, all you do is just duplicating the context object through which you go down to the database. So you have one class library and model for commands and one for queries. Having distinct class libraries is only the first step. Let's examine more in detail the command and query stack composition. In the command stack, you just use the pattern that represents the best fit. So if you have existing code to integrate or reuse, then there is no reason to sacrifice all or part of it to the name of some domain model. You just stick to it. Same if your company has bought licenses of some product or made investments in some technology. No need to sacrifice anything to a domain model, not to mention skills. If your developers know how to do something very well, it might not be a nice idea to force them away and use something else. Or at least, it has to be a very, very careful move. With Cqrs, you refresh the architecture, gain in simplicity and scalability, but without the need of reinventing the way you write actual code. The business logic can be expressed in a number of ways, as we have discussed in Module 3 of this class. So you can certainly use in a Cqrs, even in the simplest Cqrs crude-like application, the domain model pattern. And in doing so, you put your business rules right into the classes of the model. But you can likewise use other patterns, such as a table module or even a fully procedural but still effective transaction script pattern. In the end, a good domain-driven analysis is one thing, having a domain model is quite another. As for the read stack, you essentially do the same and just use the code that does the job, whatever it is. So you can use the ORM of choice, ADO.NET, ODBC, microframeworks, even stored procedures. Whatever can bring data back the way you want. Link can help in the sense that it can easily bring high-queryable objects right in the presentation layer for direct data binding. Note that an high-queryable object describes a database query but won't execute it until you call toList or another analogous method. So this means that you can have high-queryable objects carried from the bottom of the system up to presentation, and you can resolve the query right to viewModel classes as expected by the front end. A nice tip in this context is using in the read stack of a Cqrs solution a read-only wrapper for the entity framework DB context. In this way, when a query is performed, the presentation and application layers only have high queryable data, and right actions, like those you can perform through save changes, cannot just be performed. Here is some code to illustrate the point. You can use a simple database class instead of the native entity framework DB context, but wrap as a private member of this new database class the same DB context object as you get it from entity framework. Next, all you do is returning generic DB set objects as a high queryable rather than as plain DB set of T. That's it. It is a simple but really effective trick for you to use. Let's see how to implement a Cqrs design in the context of a plain simple CRUD solution based on ASP.NET MVC. There is nothing really fancy or weird to do. It's all about rethinking a few things about requests and how they are processed within a website. The key thing in ASP.NET MVC is that when a request arrives, it is captured by a controller and then processed. If the request comes directly from the browser, which means the user pushed a button to post a form or clicked a link, then the controller must return something. If it doesn't, a black view is displayed to users. If the request comes via AJAX, then the controller may even return void without affecting the user interface. From this, it sounds like Cqrs works well with single-page applications, which is true, but it also may be adapted to work with plain postback sites. Architecturally speaking, here is the dependencies diagram for a website designed with Cqrs in mind. This diagram is not a fake, but it has been created in Visual Studio based on the references of the sample project that comes with this module of the course. As you can see, the server module, the ASP.NET site, calls into read and command stacks. It also needs to reference directly externals, typically entity framework, and the purple arrows show the distinct routes a request can take, being a query or a command. This is the project solution. You see ASP.NET references, you also see external references, that is entity framework. Everything is orchestrated from the application layer, which in turn responds to requests intercepted by controllers at the presentation level. Let's see the steps involved in a query and a command. For the query, the presentation yields to the application layer, which invokes methods in the read stack assembly to get data read. Once data is back, it is stuffed into a view model for the controller to arrange an HTML view for the browser. On the command side, the presentation yields to the application layer, which invokes methods in the command stack assembly to have things done. If a visual response is needed, then the presentation just redirects to the read stack. In this way, at the cost of an extra HTTP 302, we get two benefits. First, we get a clean design in which operations are separated and involve distinct binaries and possibly tiers. Second, we implement the post-redirect get pattern, which neutralizes the possibly nefarious effects of the last post action. When a user refreshes the page, in fact, the browser reiterates the last action. If it's a post, then you get the warning dialog box you see now. Sometimes it's really risky to have this, sometimes it is not. It depends on the application. For sure, it is confusing for most users. The post-redirect get pattern ensures that the last operation tracked by the browser is always a get, and because of that, users will never see this dialog box again. Let's take a look at the concrete implementation of a Cqrs crude ASP.NET MVC website. When a request comes in and is handled, say, by the admin controller class, you see that the same request can come over an HTTP GET or an HTTP POST, and this is a simple discriminator for it to be a query or a command. So let's take a look at the display register method associated with the request of reading about a registered item in this website. So we have to perform a query, and the admin service is the class that represents, in this context, the application layer. We call a method to just read, and instead, when we post to register an information item that makes sense for the application, in the post register, we call another method on the application layer, register, and then after we have performed the command, we redirect back to the display register method to have the view rendered back to the browser. Let's have a look at how in the admin service application layer class calls to the command stack and the read stack are managed. In the get admin view model, we see that essentially the query is run through the database class that we see defined in the read stack. And the database class, as mentioned, is the plain wrapper around the entity framework DB context class that just allows iQueryable objects to be returned instead of modifiable objects, as would be the default when you work directly with the entity framework DB context. And the register method instead uses a regular classic ORM entry point, the DB context of an entity framework, to perform queries, and the DB instance here has full access to collections of data, has DB set objects, and then there is the chance to save changes back to the data store of the application. All applications are CRUD applications to some extent, but at the same time, not all CRUD applications are the same. In some cases, it may happen that the natural format of data processed and generated by commands, so the data that captures the current state of the system, is significantly different from the ideal way of presenting the same data to users. This is an old problem of software design, and we developers solved it for decades by using adapters. In a Cqrs, just having two distinct databases sounds like an obvious thing to do if data manipulation and visualization needs would require different formats. The issue becomes how to keep the two databases in sync. The golden rule of Cqrs is that you always use the pattern for organizing the business logic that best fits your needs, and this is the golden rule of implementing command stacks. I tend to restrict common choices to using domain model or transaction script. However, just the separation of commands and queries should inspire you to look at coding the command stack from a more task-oriented perspective. A command is just a statement that triggers a workflow. And as you don't have concerns as for the data model, then you could just optimize the workflow and use and persist data as it comes natural. This means ad hoc storage. And ad hoc storage, depending on the scenario, may mean something like a relational schema or schemaless data NoSQL, or even in alternative or in addition, a data store that logs business events. Use the code that does the job remains the primary rule for coding the read stack of a Cqrs premium solution. That means using the data access technology of choice, whether an ORM or other. And as it's just about queries, then link does help a lot. And so it is the feature we discussed earlier in the module, so using iQueryable of T objects instead of dbset of T. If you are, of course, on the .NET framework and you are using Entity Framework. If you feel that data is preferably taking different shapes in command and query stacks, then it mostly needs that whatever is the most effective way to store the data of the system for query purposes, you want to have ready-made relational tables. Even when a NoSQL document database is optimal for commands, queries are still best served by a plain classic relational set of tables. The issue is having distinct data stores for commands and queries makes development simpler and optimizes both operations, but at the same time, it raises the problem of keeping the two stores in sync. For the time in which data is not synced up, your app serves stale data. And the question is this acceptable? The dynamics of a Cqrs premium solution when two distinct data stores are used is the following. When a command executes, the command data store is updated. The state of the system is consistently saved within any transactional boundaries you need to have. At some point, in some way, the state of the system must be, so to speak, replicated in a format that makes it suitable for the read stack. There are many possible ways to keep data stores in sync, and choosing one or the other just depends on what's best for the application. The first approach that comes to mind is making everything synchronous. Every command triggered at the end just starts the sync up operation as part of its transaction. But if synchronous is too much of a work and also represents a potential stumbling block for scalability and or performance, then you can make the whole thing asynchronous and run it outside of the command transaction. If having stale data is acceptable to some extent, you can also schedule synchronization as a periodical job that reads the command store and updates the read store. And finally, the synchronization can be as lazy as possible and even triggered on demand. For example, when a read comes that may find stale data and you don't want it to serve stale data. In terms of staleness of data, the sync option keeps data automatically in sync. The async approach keeps data eventually up to date and does that in a matter of milliseconds. The scheduled approach assumes it is acceptable for the application to work with stale data for a few seconds or hours or even days. And then the on-demand option is a bit of everything. It's up to date, but just when you need it. The dependencies diagram for the sample application that makes a more sophisticated use of the Cqrs principles, what I have called Cqrs premium, is, as you can see, a bit more articulated than Cqrs regular. In particular, you notice the server, the central module, the website, that calls into command and read stacks. In turn, command and read stacks reference external libraries, notably Entity Framework, and also a shared helper library and the system infrastructure. The infrastructure, in this case, serves the purpose of incorporating and wrapping up the data access layer around Entity Framework, and in case also other services and frameworks. This is done to favor reuse and encapsulation of code. The Visual Studio project also offers another view of the list of dependencies. As you can see in the sample application, I'm also using ASP.NET SignalR and OWin middleware. To some extent, those can be considered part of the infrastructure too. And let's see how to implement a Cqrs premium design, always in the context of a layered system. The actual demo that comes with a module still uses an ASP.NET MVC website, but however, there is no loss of generality in that. The architecture of the solution would be the same even with another rich or mobile client and even on a non.NET stack. So, the user interface places a request and the application layer sends the request for action down to the command stack. To see the value of a premium approach, imagine that the application is essentially an event-based application, for example, a scoring app, in which the user clicks buttons whenever some event is observed and leaves the business logic the burden of figuring out what to do with the notified event. The command stack may do some processing and then saves just what has happened. The data store ends up being then a sort of a log of actions triggered by the user. This form of data store makes also so easy to implement undo functionality. You just delete the last recorded action from the log and that's it. The data store, the log of actions, can be relational or it can also be a NoSQL document database. It's basically up to you and your skills and preferences. Synchronization, whether it happens within or outside the current business transaction, consists of reading the list of recorded action for a given aggregate entity, for example in this case the match, and extracting just the information you want to expose to the UI listeners. For example, a live scoring application that just wants to know about the score of a match and doesn't care about who scored the goals and when. At this point, the read data store is essentially one or more snapshot databases for clients to consume as quickly and easily as possible. Let's start our analysis of a Cqrs premium implementation from an analysis of the command stack and precisely what happens when the front end sends a request for action down to the command stack. Because everything passes through a controller class, we need to take a look at all methods in a controller class that can handle post requests. As you can see, we assume to have an interface in which several buttons, several submit buttons are available in the form, and whenever users click on one of those buttons, an action, a request for action is posted, and it is interpreted in the controller end has an event that has happened, and we receive out of the user interface a value that identifies as a number the type of the event that has occurred and specifically the button that the user has clicked in the user interface. Now, the controller passes the burden of executing the action down to the match service class, which represents the application layer, and the process action method on the match service class, as you can see, is just a long list of cases within a switch statement. But as we scroll through the implementation of the process action method, all that we see is that regardless of the event, what we do is essentially logging an event using the helper class event source manager. The differences between the various events is only the number of parameters we pass and, of course, the values of those parameters. Let's have a look at the event source manager class. As you can see, the class is made of, for the most part, of a list of overloads for the log method, and if we take and expand one of these log methods, we see exactly what happens. The first instruction we see is a form of adaptation, so the event carries data. This data is assembled together in a class match event that we can persist as is in the event repository. Now, if we are using a NoSQL database, the same event class or the same bunch of data we receive from the user interface can be persisted as is, but because we are using in the demo a SQL Server table to persist events, we have to essentially prepare a record that can be easily persisted in the SQL Server, and this is exactly what these 2 lines of code are actually doing. After that, we need to sync up synchronously with the read model. So we have just updated at this time the command state, the current state of the system is absolutely up to date. We want to reflect this state for the presentation layer. So we obtain a domain model class. The match variable represents an instance of a match class that knows everything about the state of the current match, and we do that essentially reading all logged event for the specified match ID. We build a consistent instance of the match class, and then we just call another helper class, the match synchronizer, which essentially extracts information from the snapshot of the state and create an ad hoc snapshot for the presentation layer to read. When you think about a system with distinct command and query stacks, inevitably the vision of the system becomes a lot more task-oriented. Tasks are essentially workflows, and workflows are a concatenated set of commands and events. A message-based architecture is beneficial as it greatly simplifies the management of complex, intricate, and frequently changing business workflows. However, such a message-based architecture would be nearly impossible to achieve outside the context of a Cqrs that keeps command and query stacks neatly separated. So, what is the point of messages? Abstractly speaking, a message can either be a command or an event. So in code, you usually start by defining a base message class that defines a unique ID for the workflow and possibly a timestamp to denote the time at which the message was received. Next, you derive from this base message class additional classes for denoting a command, which is a message with a name in the typical implementation, or an event, which is essentially just the notification of something that has happened, and you can add to further derived event classes properties. They may help retrieving information associated with that fact. An event carries data and notifies of something that has happened. A command is an action performed against the backend that the user or some other system components requested. Events and commands follow reader standard naming conventions. A command is imperative and has a name like submit order command. An event instead denotes a thing of the past and is named like order created. In a message-based architecture, you render any business task as a workflow, except that instead of using an ad hoc framework to define the workflow or plain code, you determine the progress of the workflow by sending messages. The application layer sends a message and the command layer processes the message. In much the same way, the Windows in early Windows operating systems worked for years. When a message, whether a command or an event, is received, the command stack originates a task. The task can be a long-running stateful process as well as a single action or stateless process. A common name for such a task is Saga. Commands usually don't return data back to the application layer, except perhaps for some quick form of feedback, such as whether the operation completed successfully, was refused by the system, or the reason why it failed. The application layer can trigger commands following user actions, incoming data from asynchronous streams, or other events generated by previous commands. For a message-based system to work, some new infrastructure is required. The bus and an associated set of listeners are the main building blocks. The core element of a message-based architecture is the workflow. The workflow is the direct descendant of user-defined flowcharts. Abstracted to a Saga instance, the workflow advances through messages, commands, and events, The central role played by workflows and flowcharts is the secret of such an architecture. As simple that can be easily understood even by domain experts because it resembles flowcharts, and it can also be understood by developers because it is task-oriented and then so close to the real business and so easy to mirror with software. Cqrs Deluxe is a flavor of command query separation that relies on a message-based implementation of the business tasks. The read stack is not really different from other Cqrs scenarios we have considered so far, but the command stack takes a significantly different layout. A new way of doing old things, but a new way that is hopefully a lot more extensible and resilient to changes. In this Cqrs design, the application layer doesn't call out any full-fledged implementation of some workflows, but it simply turns any input it receives into a command and pushes that to a new element, the bus. The bus is generically referring to a shared communication channel that facilitates communication between software modules. The bus here is just a shared channel and doesn't have to be necessarily a commercial product or an open source framework. It can also and simply be your own class. At startup, the bus is configured with a collection of listeners, that is, components that just know what to do with incoming messages. There are two types of message handlers called Sagas and handlers. A Saga is an instance of a process that is optionally stateful, maintains access to the bus, is persistable, and sometimes long-running. A handler, instead, is a simpler one-off executor of any code bound to a given message. The flowchart behind the business task is never laid out entirely. It is rather implemented as a sequence of small steps, each calling out the next or raising an event to indicate that it has done. As a result, once a message is pushed to the bus, the resulting sequence of actions is partially predictable and may be altered at any time, adding and removing listeners to and from the bus. Handlers end immediately, whereas sagas, which are potentially long-running, will end at some point in future when the final message is received that ends the task that saga represents. Sagas and handlers interact with whatever family of components exist in the command stack to expose business logic algorithms. Most likely, even though not necessarily, you'll have a domain layer here with a domain model and domain services according to the architecture we discussed in Module 4. The domain services, specifically repositories, will then interact with the data store to save the state of the system. The use of the bus also enables another scenario that we'll discuss more in detail in the next module. This is event sourcing. Event sourcing is a technique that turns detected and recorded business events into a true part of the data source of the application. When the bus receives a command, it just dispatches the message to any registered listeners, whether sagas or handlers. But when the bus receives an event from the presentation or from other sagas, it may first optionally persist the event to the event store, a log database, and then dispatch it to listeners. It should be noted that what I described here is the typical behavior one expects from a bus when it comes to orchestrating the steps of a business task. As mentioned, Cqrs Deluxe is particular just because of the innovative architecture of the command stack. The read stack instead just uses any good query code that does the job. Therefore, it means your ORM of choice, possibly link, and ad hoc storage, mostly relational. And the issue of stale data and synchronization we discussed earlier in the module, it's still here present, and in the context of a Cqrs Deluxe solution, the code that updates synchronously or asynchronously the read database can easily take the form of an handler. At the end of the day, compared to a solution I classified as premium, a Cqrs Deluxe solution only has a richer and more sophisticated infrastructure. The infrastructure, in fact, has to provide bus capabilities and support for listeners and handlers of business logic commands and events. The bus, in particular, is a class that maintains internally a list of known Saga types, a list of running Saga instances, and the list of known handlers. The bus gets messages, and all it does is dispatching messages to Sagas and handlers. Each Saga and handler, in fact, will declare which messages they're interested in. And in this regard, the overall work of the bus is fairly simple. A Saga is characterized by two core aspects. One is the command or event that starts the process. The other is the list of commands and events that Saga can handle. The resulting implementation of a Saga class is then not rocket science. The class declares messages it is interested in through multiple interfaces, and then its body is full of handle methods, one for each type of supported message. Each Saga must be uniquely identified by an ID. The ID can be a number of things. It can be a GUI ID, or more likely it is the ID of the aggregate the Saga is all about. In general, a Saga is a process that involves some collection of entities relevant in the business context. Any combination of values that uniquely identifies the main actor in the process is anyway a valid identifier for the Saga. Also, a Saga might be stateful and needing persistence. In this case, persistence is typically being taken care of by the bus, and persistence involves saving the state of any aggregates associated with the process that Saga implements. And finally, a Saga might be, in some cases, stateless as well. In the end, a Saga is what you need it to be. If you need it to be stateless, then the Saga is a mere executor of orders brought by commands, or it just reacts to events. The point behind Cqrs Deluxe and Sagas, in the end, is that it makes far easier to extend an existing solution when new business needs and new requests come up. For this extra level of flexibility, you pay the cost of having to implement a bus and a more sophisticated infrastructure for the business logic. This is exactly what I have called so far the message-based approach. So, let's say you've got a new handling scenario for an existing event, or you just got a new request for an additional feature. In this case, all you do is writing a new Saga or a new handler and then just register it with the bus. That's it. More importantly, you don't need to touch the existing workflows and the existing code, as the pieces of the workflow are for the most part independent from one another. Finally, a few more words about the bus. You can surely write your own bus class. Whether it is a good choice depends on the real traffic hitting the application, the optimizations, the features, and even the skills of involved developers. For sure, for example, you might need at some point to plug into the bus some queuing and or persistence engines. In alternative to writing your own bus class, you can look into existing products and frameworks. A few examples are N-Service Bus from Particular Software, Rebus from Rebus.org, and Mass Transit from Pandora. In an ASP.NET MVC application designed with the Cqrs Deluxe approach, everything always starts from a request that hits the controller. So, for example, we have here a booking controller class. The sample application we're considering now is a booking application that users employ to book something like a court, a sporting court, or perhaps a meeting room. When the request for a booking arrives, the controller maps that to an add method, and the add method ends up calling the application layer, passing all possible details such as the ID of the resource, the length of the expected booking, the starting time, and then the name of the user. Let's have a look at the booking service, so the entry point in the application layer. And this is where the interesting thing that characterizes the CQRS Deluxe application shows there is a simple instruction, a constructor called to create an instance of a class called request booking command, and then the command object that is sent to the bus. The request booking command is a plain data transfer object and contains the information that needs to be passed to the handler for the command. Let's have a look now at the internal implementation of the bus. We have here in the sample application a class called in-memory bus. This is a very simple implementation of the bus that doesn't support any form of persistence. Everything, all the sagas, all the handlers, all the running instances are kept into memory. The in-memory bus class implements an interface called iBus for the sake of design, and the interface has 4 methods: register saga of T, register handler of T, send, and raise event. So what we expect to be the public interface of the bus is fairly clear. We use the interface of the bus to register saga types and handler types, and also to push a message and to raise an event. It's interesting to see what happens when we try to register a saga. In addition to a bunch of lines of code for essential validation purposes, all that happens here is that an instance of the saga type is added to the internal dictionary, and even simpler is the code we run to register a handler. And then the send method and the raise event method, as you can see, do exactly the same. So they process internally the message, but when raise event is called, in addition, the event is sent and persisted to the event store. The bus is configured at the startup of the application. For example, in this static class, bus config, that is called from within the application start event. And the initialization of the bus is fairly trivial, easy to understand. The bus class is instantiated and the event store is injected in the constructor, and then using multiple calls to register saga and register handler, we just populate the internal collections of the bus as far as known sagas and known handlers are concerned. Let's have a look now at the internal details of a saga sample class. There is a base class that we consider part of the infrastructure, so it's our own code. You find the code of saga class in the source code that comes with this module. Booking saga is then a saga, and it declares the message that starts the saga with the I start with message interface, I start with message of T. And this part of the class definition is exactly what tells the infrastructure that whenever a request booking command message is received, a new saga, a new booking saga instance has to be run and stored inside of the bus. And the implementation of the I start with message interface consists of a public method called handle, which just receives the specific command message, and what it does internally is precisely the code that handles the message, the code that you would have expected to find right here in the application layer had you coded the workflow following a certain use case directly with your own code. An interesting thing to notice back into the saga is that is the sequence of actions that we perform here. In first place, we create a booking request object, and booking request is an object in the domain model we have in the command stack. Then we persist a booking request and we obtain a real booking with its own unique ID, and we do that through a repository, or more specifically, more in detail, using a domain service which interacts with the command stack database. The response we get here contains simply a Boolean answer whether or not the operation was successful, and if the operation for whatever reason failed, we then create a new event message, booking request rejected event, and we raise the event to the bus. If everything went fine, instead we create a booking created event message and push that to the bus. Because we call in both cases a raise event, both results, whether successful or not, are logged as events. And the final aspect I want to emphasize is the extensibility of any piece of business logic that is created using the Cqrs deluxe approach. Suppose now that you want to have a chance, users want you to give them a chance to handle in a different way the situation in which a booking request is rejected. So you want to have an handler for this specific event. All you do is go back to the bus config and just add a new handler or perhaps a new Saga here in the configuration of the bus, and then you simply create an ad hoc class, and this is a sample handler class. The handler class inherits from a base class and implements maybe multiple times with different types the iHandle message, and iHandle message interface is also an interface you can have on Sagas should the Saga be able to respond to multiple commands, even if it's a running instance. iHandle message has nearly the same configuration as the iStartWith message interface. It's all about having a handle method which receives a message event and does what it's supposed to do, what it's expected to do. In this particular case, the email handler is interested in receiving a notification of a booking request rejected event, and when this event comes, all that it does is sending an email with an error message to the registered user.